What we're going to do now is we're going to, as Zach mentioned, our next part of this is going to be talking about several different examples on the comparison between 2009 and 2013. So the first one I wanted to start with was a high mass comparison here. And just a little background on that. This is a standard Excel Energy 130-foot design with the AASHTO 2009. Using one of their typical EPA's value in square foot, and the total weight at the top of the pole is 985 pounds as part of the design spec. And we used fatigue category 1. Vortex shedding was implemented as part of the design check, and the natural wind gust is part of the whole fatigue baseline for the analysis. The AASHTO 2013 basically has the same information as you can see there as the page before, but based on the chart that Zach showed a little bit ago with the map of the United States, it has to present the load case based on that particular wind pressure. So the wind pressure for this area in Colorado was, as we discussed a little bit ago, could be in either A or B, depending on what part of the state you're in or location. And so on this one, the Excel Energy 130-foot has what I want to really emphasize is it has a 23-inch base OD, and it has a thickness of 5/8. And you can see that the total shaft weight over there is 6,200 pounds on the end there. And the base plate is 33 inches square with a 28-inch bolt circle. And we have eight anchor bolts on there. What I wanted to show here is that the full base weld connection, full head weld, in AASHTO 2009 with that is classified as a 4.5 KSI strength in the fatigue. And then in AASHTO 2013, you can see that these new equations are part of it, whereas in the here is the thickness of the pole, and down here it's labeled here again. This is the diameter of the pole. This here is a new ratio that compares your bolt circle to the pole diameter. This ratio down here compares your center hole opening, which is a new part of the AASHTO 2013, and the pole diameter. And then this is the thickness of the plate. So it really, the newer code emphasizes a lot of the physical dimensions that are part of your design. That's what Zach was mentioning, that it wasn't a one design meets all for that connection. This gets very specific into the actual physical dimensions that you're trying to implement in your design. So when you put all these things into your analysis, you come up with a KF value. With that value of the 2, and you put that to the power of that KF, and then you get this KI value. And I will show you what that means in the next class. Yes, sir.
On the C, isn't that supposed to be C sub BC and then 0.2 to the point of power?
Yes, it should be a subscript down below.
Yeah, okay. Yeah.
And so, just kind of putting the numbers to paper there for you, this was still the value up top. But when you put on all the values in here was the thickness of the base section, that was the diameter of that, and here is the bolt circle that's part of that. This is the inner hole dimension, and there's the diameter of the pole, and so it is to the power of in that spot there. Then the base plate being 3 inches thick, you run out all those numbers and you get a value equal to 2.53. When you put that into this equation in here, you can see that this is the value that's in that code portion that Zach was showing, the 6.5. This answer, the answer of the equation here comes out to 7.07. So that whole section in AASHTO 2009 is no good per the new code. And that's what we want to emphasize, that there are some little particulars in there, but this one kind of defines it very specific to your pole design that you would like to utilize. So what we wanted to do is we wanted to take the pole up a little bit different in terms of diameter, a little bit change in the thickness, and we increased the base plate size and the bolt circle, and we made the center hole a little bit different to meet the new criteria, and I'll show you how that works in there. So if you put in the new data into here, we've got a little bit thinner wall for the base section, a little bit different section here, and a little bit different on the hole size here. We maintained the 3-inch plate. We changed this number a little bit from the previous one, but you can see that when you multiply it out, we just came under that limit here. And so by us being very close to this number, we have a very efficient, very cost-effective design for you to as part of your design, and it does at that point meet that same threshold value as compared to the older connection design that was just implemented as a full pan backup ring type of connection. And so you can see that the difference between these poles is not a huge difference in here, but at the very end here you can see that we're only adding about 1% more steel on that particular element. So from that, it seems like a pretty cost-effective, type of and material usage type of format. But now that we go to add the handhole ring here per the new requirement, as Zach had explained with the dimensional requirement, you can see that we added a whole new aspect into that. In the 2009, the spec had called out that the center, we take it to the center of that rim, the handhole is 26 3/8 above the base. AASHTO 2013 says that you must be 1 diameter clear distance of the pole between the base and the bottom of that. So that would really require that whole handhole to raise up in height above the base plate. And you can't exceed the 40% of the shaft width, and the 4 KSI on the net section properties of the shaft width, the handhole, as Zach had discussed before the break. And you can see that the handhole that is being used, and these are the internal dimensions for that particular design spec.
And you've got a concentration factor of 4, for the...
Right, and that's in the code there. We'll take you up to that 16.
Yeah.
Yes, sir. Yep. So you can see here that the current height requirement here, that by taking that a little bit newer design in there, the one we got to work with AASHTO 2013, what we did is I took the diameter, and then you take the position of it minus the taper rate, and you come out with an odd dimension right at this cross-sectional area. However, to get the new code requirement, because of that inside diameter being 11, we divided that by that 0.4. Therefore, your pole now increases from 24.5 to a minimum of 27.5. Therefore, we said that really, in essence, because we had to take the taper rate back into it to add it back, required us to take it down to it, because this is 27.5 at the location. So we took it down to 28 at the base of the pole. So we did the checks, and we increased it. We had to, no matter what, even increase it further to this dimension. And I will show you how that actually implements in terms of your cost. So we had to get the dimensional things, but then we had to make the spec, the checks to work. And you can see we maintained the 1/2-inch wall, and all the other sizes had to increase. The base plate had to increase accordingly, and we had to drop down to make the stresses work, so we had to go down to an 18.5-inch bolt circle, but now that's relative to the 28. So you can see there's quite a bit of added more material into that base plate to make everything implement. But the big amount of change here is you can see how much it increases here, and it's kind of hard to tell, and that's 39% increase in your material weight in that particular element. You can see that we do a check here for both our analysis in our program that can help to do checks for you, does the regular stress check of the wind, and then it's doing fatigue check, and we have implemented a new part in our program for 2013. This is handhole analysis check, and it's at 1.0, so we have really built this one to the best that you could have.
A while back, I don't know how many years ago, but there was a microburst out at the airport here, and Valmont had quite a few high-mast light poles, and they came down. It was all attributed to, I think, to the microburst. I don't know, there was a lawsuit, and that was between you guys and the airport and all that. But out of this, you guys went to Lehigh University, and you had some research done there to, you were trying to salvage, you were going to build new bases. I think that was what was on your mind, and you did. And you came up with really good stuff. Now, can I assume that what you're showing us here also incorporates what you learned from that microburst, because you solved the problem?
I believe so. I don't know as much on that. Zach, do you have any other information on what that, how much that was implemented and that research that was taken with the Lehigh stuff?
I know that Carl McKetto was involved in their NCHRP study. I mean, Roy ran it, but you have a panel that gives input throughout the whole process and involvement on, okay, what designs should we be looking at, kind of what are the industry standards. So there was some feedback. I don't know exactly how much the exact details of that were actually implemented in there, but...
well, that was private information. I mean, you guys, you were in a lawsuit and you hired Lehigh University to help you, and they did. But my understanding was that you made thicker hole at the base,
Thicker
the
base
base
section.
section.
yeah.
It was a thicker base plate and a thicker base section.
Yeah, and all that goes with the current code too. Thicker base plates are
Right,
part
right,
of the new
right.
code.
Yep.
And then the thicker
Because
base
that-
section making the checks that your program makes, right?
Right.
And make all that work. And so that technology, it's all here too, right?
Yeah, but I mean, part of the point, or maybe the point you're making, is the poles that were supplied met the AASHTO code at the time.
Yeah.
And then now, I'm sure that's part of maybe why some of this stuff is getting looked at.
Exactly. That's my point. That
Yep.
Yeah.
You learn from the past, and
Yes.
what we're seeing is the benefit of all of that.
Exactly.
Yeah, okay,
Good.
good.
It all kind of compiles together.
Yeah, right. So in other words, if you designed the same holes to go back out at the airport today, you'd use that right there.
Yes, sir.
Dick, I'm Jim Drush from Region 4. Was this the same kind of deal with the high masts we had up there from the winds or tornado, the ones that were, the base was cracked, and they come up with that sleeve?
Yeah.
Is that kind of the same thing that happened up there?
Yeah, it's a very similar thing. And I can't remember, was Valmont, did we work with Valmont?
I can't honestly remember. I think it was Valmont.
I think
They
it was
came
too.
up with that fix too, that it was a thicker sleeve put down to basically reinforce the base of the poles.
Right, and you had to have, it all goes together. You have to have a thicker base plate, you have to have a thicker pole section at the end. All that leads to these checks that work now with the new code, and the knowledge from the past is presented right there. Marvelous, good.
Yeah.
One thing that's interesting to add is you're talking about the thicker base plate and the thicker shaft. You actually have, you decrease your shaft thickness, you actually get more fatigue allowable stress. But obviously your section properties go down, so your stress goes up.
Yeah,
But as you decrease your shaft thickness, that K sub F equation, K sub F, will go down. And so as you get down lower, down to 4 or 3, you start getting 7 KSI and 10 KSI allowables. So you want that, you ultimately want is the ratio of the shaft to the base plate thickness. You want that to be, your relative, more stiffer base plate than your shaft to get a better fatigue
Right,
resistance.
right, because if you don't do that, you have a very thick object and you have a pipe wall trying to do that about a surface it can't bend. You don't want any warping anywhere. You gotta get it, that warping, distortional fatigue is the issue, and thicker is the answer.
Right,
And
and
so
you see
you
that
come
right there
up,
at the end there on that very.
Right.
part of the equation, yeah.
and so when you come up with 39% more steel, or that's what you were showing, right?
Yes, sir.
Something like that.
Yeah, 39%.
And I'm saying, yeah, perfect, because that was the answers you guys came up with your airport experience.
Right.
Yeah.
I don't want to get too far into the engineering, because that's not my background, but your point is well taken, that whether it's in the sports lighting arena, there's been some things that have happened down in Texas, whether it's in our comm experience, whether it's in our high mass experience, we're always plowing what we learn into design programs to make what you guys are getting in the field
Yeah,
more or less.
yeah, and the fact that that is more, that doesn't bother me one bit. It should have been more to start with. That's my point.
Yeah. Okay. And so the next one that I wanted to kind of work through, because fatigue is a big part of traffic structures also, is to do a comparison between 2009 and 2013 on that one also. So the background here was I'm going to use a standard, I should just say a 35-foot mast arm example with signals and signs on it. And using AASHTO 2009, I had 2 signals and 2 signs on this particular 35-foot design for a total weight that was along the entire arm, so it wasn't centered at one spot. In that particular spec, we went with fatigue category 3, and you would have the natural wind gust, but also the spec required that there were going to be no truck or no galloping on those particular elements, and we can discuss it a little bit more. AASHTO 2013, basically I followed about the same criteria in there, and just went with the same design parameters, trying to do about the same. So the 2009 design, what I wanted to show here, had a 13-inch 3-gauge hole, and for a shaft weight of about, with the arm, about 1,400 pounds. Base plate was 18-inch square and had about a 17-inch bolt circle and 4 bolts in there. I went through the same type of design process, same equations as what we had there. Bullpen backup ring connection there, and it had the same equations as you just saw below. We had the subscript issue there too. And then when I put in all those variables in here, I came out with a design that showed that this value, as we put in here, worked into the equation, and it was good for up to 7, even though it might not be necessary. It was good for up to 7, but it gave you a more defined answer than just the overall just generic one that was in AASHTO 2009. So you knew that you had a little bit more strength in that particular design. What I maintained all that type of thing. I put in a center hole, which was different than what was on the 2009, a little bit different diameter hole. I ran through the numbers on that, and it showed that it worked with that new design. And I'll show you, because that was with no handhole rim that I increased, because the plate sizes had to increase on the base plate primarily. I had to increase the weight was about 2%. And that was without the handhole requirement. So next, if I add a handhole on the same format as we do with a high mast, it's centered at 18 inches and going through the same process, the 1 pole diameter, the 0.4, the 40% of the shaft, and then the 4 KSI on the handhole rim. But in AASHTO 2013, with the traffic structures, we have one at the base And then we have one up at the mast arm location, and in this spec, we use the that same handhold is located at both spots. So the one is at 18.28 minimum above the base plate, whereas the other one was just centered at that as per spec. The other one's at 18.5 because that's what was labeled in their spec, even though the arm is up at a higher elevation. And so I was just meeting what was on that spec on that particular design. And you can see here that the minimum height has to be taken off. The design has to be taken off of the upper handhold, not the lower, because of the taper dimension. So based on that, the handhold, if I stayed with the old 13-inch diameter pole, I had to go down to 10.4. However, using the spec handhold here, you would have to increase by a little over an inch in diameter. So therefore, the current design does not meet the AASHTO 2013 with the handhold dimension. So we had to increase this to 14.5. And so it kind of shows that it proves that your new design is going to be 1191 compared that to 1158. So you can see that we do meet the code. And then based on implementing all of those type of dimensions and changing in the center hole dimensions in there, we had to increase the design about 19% more steel on that particular design. And so that's the effect between AASHTO 2009 and 2013 particular design. And so there's just some examples that we want, some key things to think about on this, that as Zach had mentioned, owner has the ability to approve different handholds that could potentially fit into that. The stresses at the check are more in depth than the old, with these variable dimensions, allow those equations to give you a more defined stress value. The center hole opening minimum, and this could affect how, based on those smaller dimensions, based on your requirements for conduits and other wirings and other things that need to go up into the particular pole, is that hole opening large enough to provide all the electrical room that you need for getting that electrical stuff up into the pole. Is there any other particular questions before I move on to my last example?
So how big was the hole in that example then?
On this one here, our standard here for it's on the standard one, I just let the number run itself out. We would probably run that to 11.5. And I left it as 11.5 work for that particular design, as you can see the stress did. But since we did increase the pole 1.5 inches, it was allowing us to increase this size here. So that was a benefit of going to the 2013 on that if you were worried about how much opening dimension you would have in these at the base, that this 12.5 dimension was a little bit bigger, even though the pole got bigger. So you can see that the stresses allowed it to get just that much bigger.
So what, two more questions, what did that to the cost, and what generally are you using for design line?
That one still met the requirement here. It kind of gave you this, the old code would have been a 4.5 based on the full pen backup ring, but this fit in the code. It's 3.87. If you look in the code range there, it does allow for a 7 KSI, so it did give you a little bit more stress range characteristics, which is a good thing. Even though it wasn't required by code, we only needed to meet 4.5, but this actual section design here and how it was modified did allow us to go up to a 7. So that is a benefit, or at least it did put more analysis to prove that it was a good connection.
And cost?
That would increase about 19% for that entire section, because we had to go from like 1.5-inch plates to 2-inch thick plates, as per what Zach had presented at the very beginning.
So the cost, you said, is 90% based on percentage of steel, or is it something higher?
I don't know the exact cost difference. I know just material amount, the weight increased by 19%. I couldn't tell you on that. That might be for Denny
Well,
and
but
for
the labor,
Ryan.
the labor is, you know, I don't know if it's 50%, I don't know. I mean, the price of the pole wouldn't go up 19%, because
That's what-
that's only the material, but the labor is probably comparable.
Just
right?
try to get sort of an estimate of, you know, how much it's
Yeah.
going to cost for this coach.
You know what, we can price it up and let you know, and you can make your decision that way, yeah. I don't know.
So
Maybe
it is
half.
more of a material cost, material weight increased by 19%, so those variables on the cost.
Something less than 19%.
Yeah, ultimately, I would say it depends on how much the weight comes from the plate as opposed to the shaft, because those variables drive the overall cost of the item. So to Debbie's point, different items are going to have different ups or downs.
Here, just from a rough standpoint, really rough, because what you bring up is the plate versus the pipe. But if you just said that half of the cost is in, I don't know that you can do this, only you guys would know. But say half of the cost of material and half is labor, then that material cost, you're still gonna put the same amount of labor in, so it's not as bad as it looks. What I'm trying to say.
Right.
But you guys know what the break.
Yeah, I'm guessing in the 10% range, because you have to also consider
That's
transportation.
what I would have said.
Yeah. Time you put all that stuff in there, it isn't as bad as it looks.
Yeah.
Yeah.
One thing to add to that is we don't talk about it specifically on there. We've ran into in some states, as those diameters get larger, you got to think with the lowering devices. We actually had a state where they followed this to the T. Their sections got even bigger. To follow the coach to the T, their section went to a 36-inch diameter. So their lowering device on the 100-foot pole would get down to 70 feet, and it couldn't go any farther because the diameters are too big. So kind of think about the implications on the other end of it. And then back to the center hole size. This example, I guess we didn't have ones that really showed how the huge difference. But sometimes we've seen high mast poles we designed with a 26-inch diameter. The center hole size is around 10. So that's when you really start having that issue of, in the old code you'd had about a 22-inch center hole. Now you're at 10. Make sure the alignment's real good, or else there's gonna be a problem.
And one thing we wanted to note too, as part of that, especially on the example here with high mast, was that since it did change a fair amount on the diameter, that your foundation cost would go up just because they're going to get bigger to meet the corresponding new dimensions. The last one I wanted to do was just a quick comparison of our camera pole, and this is between 2009 and 2013. So there are some that are like 40 to 70 foot camera poles, and the camera pole designed for 2009. It had 6 camera and equipment loads on the pole. So that was in 6 cameras. It was 6 items that were on the pole for a total weight of 290 pounds on the whole dimension of the pole. T category 1 was in the specifications for those poles, even the ones that are closer or less than the 40 foot. Natural gas being part of that. And obviously with truck, there's no truck or galloping in camera poles, and all the, just like the high mast type thing too. And the full pen weld with backup ring provides, as mentioned on the other design, what did have the 4.5 value. With the camera pole designed in 2013, basically had the same information as I just presented, and there were no changes really in the pole or the base plate sizes. The full pen weld with the backup ring provided, in this case also, the 7 KSI value, but we had to have a smaller hole to attain that value. and that didn't increase that much different than what the older 2009 did. So in some cases, the 2009 and the 2013, if you had a really decent design on the 2009 design, you will not see maybe any changes in weight and thus those corresponding costs. So I just want to bring up that in some of these aspects, it didn't matter. When I put in the poles were big enough that the hand poles that were in that specification all fit within that parameter. So even with putting that 40% part of it in the equation, the poles at the base were big enough for meeting the physical requirements also. So we wanted to show where it did make a huge effect, where it made a reasonable change, and then we wanted to show where it did not make any kind of an impact on going to the new code.
Is this a reflection on the fact that the camera pole has to be a lot stiffer so the picture can be seen? And so
That's
you
probably
get
where it
stiffer,
started.
you get
Yes.
bigger, and
Mhm.
it doesn't matter.
Right, and so the base plates were bigger to begin with. They met the code criteria because they were 2-inch diameter, 2-inch thick base plates. So meeting that requirement, as Zach had presented earlier, the 2-inch minimum was maintained. And so there was really no change in that, just there was a little bit difference in, and I didn't really run a cost difference, but there would be a minor change because of the smaller hole. But because it was a camera pole that did have some deflection, probably characteristics in that, I didn't know what that value was, but based on that design that we took, it did satisfy the 2013 pretty well. So we wanted to make sure we kind of showed kind of a full range of the scope of what the impact was on AASHTO 2013. And so I wanted to go into the next part here, which is kind of talking about vibration, fatigue, and some of the new fixtures that are out there, and how that kind of plays into AASHTO 2013 directly, but there are some aspects of that would apply for both 2009 and 2013. Kind of overview, whole vibration and harmonics. I wanted to kind of walk through just EPA and what that meant, and then kind of go into a real quick, just showing some of the first mode, second mode vibration that you'd see typically on poles, the vortex shedding, and then how mitigation is kind of mitigated by reducing down the vibration by dampeners. Bridge inducing vibration and how that kind of affects the wind-induced vibrations. And I want to kind of go through the fiction that is, there's perceptions and realities and engineering thinking on some of that, so I want to talk about that. Signs that your pole may be experiencing vibrations from physical, look to, from cracks, the pole moving around, and the fatigue cracks at the base and at the hand poles as things you can visually inspect. And a part of the vibration, site conditions are a big contributing factor to how that affects a particular pole on a certain site.
That third bullet up there, first and second mode vibrations.
Yes, sir.
Carl's shown us some stuff where your high-max lights have actually gone into third mode. You don't.
I just kind of kept it in first and second for today's description. So there are more modes that can occur beyond 1 and 2, but I wanted to just kind of go with these two to show. And we do have some cool videos of some of these hitting some of that type of stuff.
Yeah, where it hits the third.
Yep. The new fixtures, wanted to talk a little bit about that, and we'll discuss the reason why these variables are important to the new these designs on poles. Okay, the EPA is the affected projected area of the object, signals, or signs, and then that's just the area exposed to the wind, and then the drag coefficient is the efficiency of the wind with that object, and AASHTO has a lot of different variables that are based on the shapes of the poles and objects that are in there. And the drag coefficients are determined by experimental studies, wind tunnels, etc., or published literature that's been done by a particular light manufacturer may have done testing of a certain sort to give that value. Signals have the vertical projected area, and then they also have a horizontal area that's on the underside, and I'll explain that in a minute. The weight is important in these designs, and you have just a standard signals, and what's being used a lot in Colorado are these new programmable signals, and I wanted to kind of bring that in there, that Valmont is taking the data that you provide to us and making sure that your structures are structurally adequate to handle those particular new programmable signals.
Is the horizontal EPA, is that true for the United True. The horizontal EPA, you're talking about there, is that true for luminaires? Or is it just
On the luminaires, have, as we take the EPA and we add a certain value to that, which would encompass the horizontal and the area and the air. The vertical effective area also on the signs, and then the weight of standard signs, and then the programmable signs. And as you guys are using here, these BOS type of signs that are being used, and then I kind of locked in that you have the DMS signs and the VMS signs that have a lot of vertical, horizontal area on those particular two that would add a little bit more fatigue onto structure. And I'll mention that here in a bit. The shapes, like in the round profile, like the drag coefficients kind of vary, but a good one is about 0.5 for the round one. And you can kind of see that if you have either poles, signs, signals, and luminaires that are more in a square type form, you can see how the drag coefficient really increases. Now that really adds to your overall design requirements because your whole EPA loading goes up quite a bit. So just a real quick one to mention, like I said, just the two loads. The first load vibration is where it kind of swings back and forth, and that's the most common type of vibration that we see most of the time. And just going with the second load, it's a little bit less common, but you can see how it kind of shifts from being all at the top to kind of affecting it down the position of the pole. And I want to run. One thing I wanted to show on this here, you can kind of see how it's kind of going back and forth here. So with the vortex shedding on that, push on the pole, then it's kind of flip-flopping on each side of the pole, and that's what's kind of causing that intermediate vibration in the pole. But it's going back and forth on this thing, and you can see how it kind of moves.
Now, this is a plan view looking down.
Yes, sir.
What's the fluid mean, or what you're filming? You film something, right?
Yeah.
Is this a computer recreation, or is this actual?
I think it's an actual test that was done with that.
I'm curious, what is the fluid?
I'm not sure what that
This
is on that.
is one of the videos we work with others in the industry for a presentation, and we borrowed. I don't know if it's just wind with some sort of smoke in there, or if it's like a liquid, but it's showing the effect of like how the vortex form in vortex shedding.
Yeah.
Because we've seen images, but it's kind of interesting to actually watch it happen in live. I mean, it's not something you see too often.
And there was one point too where they thought that on a tapered pole they would never do this. But I think Carl found and filmed some that do it, proving that works. Right?
Yeah, the code mentions you have a taper pole that it's less likely, because what happens is you have to have a critical diameter. Every diameter has a different wind speed that will start this effect. So as your diameters change, the critical wind speed is only over a short distance.
Yeah.
So,
And the square pole, you definitely would have that square or around non-taper. You would have more of that that would be constant all the way top to bottom, whereas like you said, it would be more variable on the taper. So the tendency of any of these poles to develop kind of a resonant vibration. The square pole has a lot more tendency, as we've been talking, to have a higher level of ability to vibrate and the stress concentrations on those corners. The round, straight round would be a little bit less, but since you have that vortex that could run that entire length on that one also, it's a little bit better, but it's still on a high possibility of it vibrating. The round taper obviously is going to do a lot better because it will break up that vortex type of load a little bit more. And then I wanted to kind of show, just to show for like more of a utility use, and we use that a lot in Nebraska, is that we have embedded poles with a round taper pole here, and that one we seen an event of the lower, even the lowest side, partly because the ground is providing a deadening effect to resist any vibration, and it deadens it out. So I want to kind of show 4 different types of structures that show that.
I know you still can't do, but does the material impact on this change? So a square aluminum pole or a square fiberglass pole is more likely
They would
than steel pole.
it would exhibit similar type of characteristics.
The material is not seen. Does the material impact?
It would exhibit a little bit different, probably, characteristics of the vibration of aluminum or composite, but you still have that same effect of that. How it would affect it, you may have to have a bigger pole to resist that vibration.
Some people say steel poles don't vibrate as much as aluminum poles. Is that true? Isn't the material factor?
Yeah. And with the square poles, because that stress concentration is a big factor in design on that. Does that answer your question on that?
No, so everything else being equal, for a round taper pole, is it not a steel fiberglass? Well, as far as the vibration.
I think that the vibration is going to be different on there. I don't know what the difference on what that percentage amount is different. Obviously you have your material characteristics of steel versus composite or aluminum. I don't know what that variable, if it vibrates twice as much or 10% more.
What's going to matter is your aluminum's lighter, so you have a lot less resistance to keep it from starting vibration. But I mean, that's also going to change your frequency to hit. So it's hard to say that it's going to be more like it'll start at a different wind speed than your steel does, because it's a much lighter structure and it's going to take longer for it to stop.
Does the critical wind speed then rise with diameter?
Well, your VCC is dependent on
the
diameter.
wind speed required.
I haven't looked at it that close, but yeah, your diameter, that's what changes the critical velocity. I can't remember if it's a higher wind speed, higher diameter, if it's vice versa. I've seen the equation, I just forgot it.
See, there's another thing too, and that's the modulus of elasticity of these materials. They're deflection. So they're computed with moment curvature. And the lower the modulus of elasticity, the less likely you're going to get, it can't react as quickly. It's the deflection.
The reason I'm asking you to also aluminum pole manufacturers, they say, when I find it using aluminum, it's not vibrating as much as steel.
And that, I think that the aluminum versus the steel, because of that weight thing, it just kind of changes the whole characteristic of that wanting to vibrate.
And your modulus of elasticity,
Right.
I would also add that where we've seen historically diameters, wall thicknesses that exhibited this problem, they automatically get a vibration mitigation device before they even leave the factory. Right? So where we've experienced it, we're trying to assist you in providing that product that's most reliable in the field. So if you look at our literature, you'll see an asterisk or whatever next to the item that says this comes with a dampener recommendation.
So, going with dampeners, there's nothing particular to this, to any of those, any particular design, but we have this chart that we've done as testing that showed that the vibration that you would have without a dampener, and that when you do add a dampener into that design, it does reduce down a fair amount of that deflection, either on the steel or the aluminum side, as Ryan had mentioned. So we sometimes, say that it may be, a good idea to add one of those type of devices to resist or to help dampen that out faster. For traffic mast arm structures, it is using a horizontal sign blank, and we place that near the end of the arm. That's used to reduce the galloping mode of vibration. And when I was mentioning that back before, a few slides back, talking about the horizontal area of the signals and on the DMS, BMS signs, that when vehicles go underneath the structure, it puts a lot of upward wind pressure on the actual structure, and you get that type of structure to move. So I'm going to show a video here that shows how what happens on a certain pole. And it's very interesting here that you can see this one just bouncing crazy all over the place, but the one behind it back there, look at that one, and it's at the same intersection, same direction. And so this whole vibration thing is a very weird situation. We want to make sure that you saw how it can make a lot of difference in that case. The next one is just the regular area lighting. Dampeners that we have is chain and cable weighted, and canister types also, and we place those like at 2/3 of the pole height. I think those types have been used, and as Ryan has said in our catalog, can be added as part of your project.
You show the two poles there, one vibrating, one not vibrating. We recently think we've discovered that part of the problem is in the foundation. Foundations, although built the same, aren't the same. The anchor bolts in one were loose this way, and it led to damping, natural damping. And if the anchor bolts are tight, it's not loose bolts on the connection, it's the concrete didn't get, we made a pocket underneath one of the anchor bolts or several anchor bolts, just the way we poured the concrete, and it allowed the anchor bolts to slip up and down in the foundation. It made a natural damping system, so instead of being there, we thought we ought to pay the contractor more money for what he did.
So I just want to present some of the ones we feel do help to mitigate that to a lower level of vibration. Bridge where you have light poles or other structures on there, it is less common because you may not have, in a lot of cases, where you would have a light pole or that type of thing mounted exactly on a bridge. But there's also, in this case here, whereas the other ones don't, other near foundation, a vertical component that adds and can add to this pole vibration part in addition to the horizontal ones that are being caused by the wind. And it's pretty damaging to lighting and fixtures and to the structure in itself. And these accelerations can range between 0 and 10 times the gravity in the acceleration. So it's pretty powerful force, that can be added based on when something is mounted on a bridge. And generally, the most of that motion will happen in between the spans where you have just the bridge deflection, either under dead load or when trucks are going over that over that bridge. It can actually add and start some kind of a vibration motion happening. And this report evaluate how that would happen on that. We want to talk a little bit about the wind-induced vibrations, the facts and the fictions on that. Wind-induced vibration is a result of a unique combination of local and site conditions, micro-wind patterns, fixture geometry, and pole geometry. And then we kind of discussed some of that with what we were just looking at. And it's harmful to the pole and the fixture if this is left unchecked, because you could loosen up either the pole or you have trouble with the fixture. The induced wind of the vibration happens in these moderate winds between about 11 and about 45 miles an hour. A single impact of a pole in a small subset. I have that same video. I'm not going to go into that one. It's the same as that we just showed. And then the fixture orientation can influence the potential for where it is relative to the either the square, like a square pole, or wherever it's at, or a round pole. Shorter pole top poles can increase potential for the vibration. Poles should not be standing without a fixture, because if the pole is just there all by itself, or even a structure with a mast on it, no loads on it, it doesn't want to dampen itself out. It can shake itself to a higher vibration. Wind-induced vibration generally, fatigue cracks grow and propagate with any additional load cycles. Excuse me. Some of the fiction and what we have seen is that wind-induced vibration is a result of the defect of the design. And that's not true. We design these things, when Valmont does our designs, we design for stress, we design for fatigue, we design for pole deflection, for like camera poles as required, or any other deflections that's in the spec. So these things just happen as it is. Is it highly predictable? As you can see in some of those, that one little video there, it was just, we wouldn't anticipate that one happening and the other one didn't happen, either with or without the interval. The vibration dampener completely eliminates vibration, and that's not true. We've done testing. We've seen other tests. You can see where we've shown that a vibration dampener does help to reduce down the vibration, but it's not a cure-all. It's not something that you say, all my vibrations are gone. It's not that. It's a very, very unpredictable type of phenomenon with the vibration. And then we want to put in here that if you design, it kind of goes with the part up here, that if you design for the peak wind of, based on the AASHTO code, 70 miles an hour, AASHTO 2009, would be at a higher range. These 100 miles an hour, 110 mile an hour designs, that should help to reduce that vibration. And that is not the case, because you can see that was a pretty long mast arm that was designed to handle stresses and fatigue, but it still was bouncing all crazy all over the place, as you saw. So we want to make sure that you saw that even though it was designed for, that particular one was designed for 100 mile an hour wind, and it still was bouncing around. Signs that your pole would have problems, you have detection of the vibration that early can help to prevent damage to the pole and fixture, a scheduled maintenance and inspection program that you would have with your department is a very good thing for watching structures, inspecting them on an annual basis, just doing visual inspections or way up front. Pole movement, obviously, is a very big clue right up front to see just that pole movement as you saw. The rapid shaking back and forth, directions, the wind vortex shedding. You can see how that one is just a video of that.
So is that a one season?
Yeah, it's looking for between the lows. Just large cyclical pole top displacements coupled with looping action. You can see that, and show that one. You see this one's kind of doing mode, type mode 1, where you can see the top is just kind of, the low wind, just kind of going back and forth a little bit.
I have a question. On your studies, as far as, do you guys ever test them with the aluminum, let's say 40-foot steel aluminum, regular transformer bits? Does that help that? Does that hurt it?
No, I think that typically, since that would be fixed about the same way as that, there may be some physical dimension on that, how it's attached to the top of the T-base or to the anchor. There may be some difference because you are bringing that element. The T-base does probably, in most cases, have a bigger section property than the base of the pole. So it would have a little bit bigger section, so it would help to have a little bit more, or reduce down a little bit of the vibration potential. I don't know. I don't have that much on the testing side to know. I don't know if Zach has any additional information on as a T-base to that, if it would add much to that. Pole caps coming loose from the top of the pole or falling off, obviously, is not a good thing either. But you can definitely see that even though they have an issue on that particular pole, sometimes that you can actually hear, maybe not so much of it itself, but you can hear the wires inside slapping against the side of the pole, maybe a little bit more than you would think otherwise. And that would say that if you have the engagement of the dampener, like the canister type or any of the other ones, hitting the pole or working in its function can add that it's really, being utilized to try to do its work. And the rattling of fixtures or other types of components on that. Just one more on the fixtures. You could have the lamp, the light, could break because it's been shaken around so much. Broken pieces of the fixture, doors, the handhold ring doors, loose attachments to the poles or physical damage at mounting, breaking loose or the bolts coming loose on that. You can see here where the top of the pole is cracked, right at the location where these fixtures are at. And that's a very physical and a very visual, type of thing that you can actually see. Actually, the toe cracks at the base of the pole, you can see that cracks develop here, and this is a square pole, where there's a lot more stress concentration. And you can develop the cracks here, and you can see a little bit more up here where there's an actual crack. The weld is kind of breaking up, on that square pole. That kind of adds where you actually can see the fatigue, cracks in that. Also check your handhold rims and other attachment points for that. And what do you do if you find that? Well, Valmont does have, with having in addition to your maintenance and visual and inspection processes of your department, that really helps to determine these type of things either after it's occurred or hopefully before, so fixes can be made. But Valmont does have our MATCO service department, which we can come out and do inspections for your department and help you in any fashion that we could do.
I'll add one thing to that. It's not necessarily always the case of replacing structures. We talked about it in the sense of COM. There's a lot of field fixes that can be done. So you don't have the entire expense to replace the entire structure. You can maybe go to a collar or otherwise a repair of something that you see as damaged like this.
And site conditions, this kind of like a flat area here, that really can whip in, to add to where that could really make a huge difference, that where you don't have any wind get broken up, you're going to get those straight line winds on there. The vibration can occur anywhere. Some sites are more prone than others. So I just look at the map, kind of where we were talking about earlier about the high mass map. But we have seen a little bit more probability that it has occurred in this area, as we had discussed earlier, but it does happen up here and over here. So we just wanted to kind of highlight that, but it's not a little bit more prevalent, but not exclusive. In mountain areas, because of just the way the wind can come in, like you had mentioned earlier, can really affect. You can see that this steel square pole or aluminum, maybe that's aluminum, square pole broke right off because of the fatigue that was and the vibration that happened on that particular pole in this area. The one reason why I wanted to bring up this now is that because all the new technology with the new fixtures and stuff like that, it gives us a new set of variables that we have to deal with on these poles. We have lower EPAs, lower weights, which that is, as we've discussed, makes the pole to vibrate more because you don't have that dampening effect of at least a fixture with a heavier weight. And what does that mean for the pole? Common pole selection, considering only the static loads, the lower EPAs and fixture weights, you would get a smaller pole and a smaller wall thickness. But does that really help you in your vibration design? Lighter poles increase that potential for vibration-related issues, if not properly considered. This can aggravate even by adding even taller, slender poles. So all this really adds a lot more issues to either new poles, and we also want to say that if you have field retrofits with new fixtures being with less EPA on existing structures, swapping out the fixture changes, the dynamic characteristics of the structure need to be reevaluated and looked at a little bit carefully due to the effect that you may not want to move a smaller pole or smaller width thicknesses just because you put for newer structures, but the existing ones you would have problems with the EPA being smaller, that your existing structures with the heavier fixtures, you put on that newer one, it may act a lot different than you had previous.
So, from retrofitting existing fixtures, do I have to go right in with the EPAs where you can farm or deny whether it will be okay? I mean, is it going to account for vibration in pole design or not?
I think
If I'm going to go swap out my HID, it's going to need to write in the EPAs.
yeah, and that will have an effect, by
I need to quantify that.
yeah. And I couldn't tell you what that increase would be, but
There's nothing that we can do to predict if it's going to vibrate. So for providing us with it, we'll do a static analysis. We'll show if you're small, low, your structure's still good. And what we're really suggesting here is if you're going one of those new fixtures, do that visual inspection pretty quick thereafter and on a more regular basis for a while to make sure it's not going to start vibrating. Because we can't predict if it's going to vibrate or not. We're not going to be able to say in any analysis that, yeah, that's going to vibrate if you put it up there. The big thing is really be careful. Don't just put up there thinking a smaller EPA, I'm good to go. Really consider, come by 3 months later, 6 months later, and at least doing a visual inspection, let alone really looking at the welds just to see what's going on.
And I'll add one thing too. I don't know if Steve can go into it in the future, but Valmont has spent the last, I'm going to say 12 plus months working in conjunction with other people in the pole business to develop recommendations for these new installations, LED retrofits, things like that, and what happens when you get to say a 0.9 EPA fixture. to the extent that we've made a presentation at Light Fair this past year, again, along with our counterparts in the business. So there's emerging data, I think, all the time, and maybe some recommendations to come in the future about how to really behave when you're doing your retrofits.
So, even if it wasn't any retrofits, will the EPA be part of my board? I mean, okay, so today I'll give you a 1.9 EPA for my, so if I give you a 1 EPA, is that going to should be all specs, all support material, or?
I mean, if you go to the lower EPA.
Yeah. So moving forward, say, new poles, right, with all EPA feature, how is that going to impact my car?
In essence, from the design of
I think it's going to
whole
be
static
static.
points. Yeah. From the static points, you would be able to reduce down that pole size. But I think that, you know, we would have to, you know, seem to want to evaluate that, you know, because if we go too much smaller with that, then it does really, and not a exact section modulus change, you get that much more vibration. It's very variable on what that, how much it may add more to that. So having that inspection of that to see if maybe having to add more dampers to that. Yeah.
So I guess for these lighting switchovers, I guess like exposed area and weight, what are you going from and to? And I guess how does that compare to like some of our like video cameras? They don't weigh much and they're not that big.
Right, and so you could have the same kind of thing with that too. I don't know how much difference you would have on a lot of those if you're going from a very big fixture that you had, very big camera that you had in the past, and going to a really tiny one, and that may be part of it. Some of that may be handled based on, because you're adding that added deflection criteria into your design, that it may help to mitigate that, whereas on a regular light pole, then you're not going to have that actually helping you in that event.
Yeah, so I guess conversely, if he's going to smaller fixtures on existing poles, if it was a new one, it would be like over-designed because he's putting a smaller, lighter thing
Right.
on an existing pole. He's not going to downsize the pole because it's there. So maybe he won't get into vibration problems getting a smaller, lighter thing on top from what it was because it's
Right, you have
over-designed.
smaller
in that
EPA,
sense.
but you could have more vibration. So there's something that we have to wait, do some kind of a wait and see type thing or some of that.
Would you guys make a recommendation, like for a bay, if you guys did a calculation on that, if he changes from an EPA of 1.8 on a fixture to say a 0.7, should he be putting a vibration mitigation device into that pole at that time to protect himself going forward?
It probably would be a good suggestion.
Can you guys
There's
make
no,
a
there's
recommendation?
no calculation,
There's
and
no
we would say
calculation.
yes. Anything below 1.5, and that's what I think was suggested at Life Fair. Anything below 1.5 is a suggestion for a dampener on it. There's no calculation to check to say, yeah, this is it.
And those are square footage of exposed areas, or what's the?
EPA.
That would be EPA change, you know, but how that really affects it, you know, from a stress it would, but for vibration,
Do banners,
for banners.
banners, are they considered dampeners too? Or is it just weight as far as dampening vibration?
We take that more as
That's a wind
as a
limitation.
wind, and it has a lot of EPA. There's not a large amount of weight in there, so there is that little bit, but we would believe that in a lot of our cases where we're doing banners, and we do have like breakaway banner arms to that when you get over a certain range, then it would break away. So that EPA would go down, therefore your stresses would go, not knowing how that really adds or takes away from vibration. I don't know.
The reason I was asking, sounds to me like dampeners, for an object or an attachment to qualify to be a dampener, it's really driven by weight, not necessarily the area. So a fixture's EPA reducing, does that impact dampening or vibration, or is it more the weight of the fixture?
The weight does help because
Is it weight or area? That's the question.
the weight would help more to dampen it than the area.
So I should be more concerned about the weight of these LEDs and the
Yeah, and some of that was based on design. So if you had your EPA and your weight, so when we're doing our design check for stresses, that would be in there. For the weight, having that weight in there, if it was heavier weight, that would dampen a little bit more than if it was less. It's the dampening motion.
There's something else to weight does too. If you look at high mass lights and you look at the lighting fixture at the top, it weighs a lot. You go stand under the pole and look up and you see the top doesn't move. Oftentimes the top isn't moving. So you might go into second mode, and if it's really windy, you might go into third mode and the top won't move. If you take the weight off, it might try to go into first mode. The weight has an effect on the mode, your modal shape. You see, it's like pinning it, if I had it. And so you take that pin out, now you can try to just do that. Given condition, of course.
And where we've had that, you know, is that we've had where even a mast arm that did not have any loads on it.
Yeah.
And it was not, something was not put up when it was installed. And the arm in this particular location, in this particular stage, was a 60-foot arm. They did not put up any signals on it. That within the week, that arm, which was designed for fatigue, for loads with like 5 signal loads and signs, came down.
So that's
because
interesting.
everything vibrated itself apart.
The arm is heavier than the signals, right? So you think
Right.
dampening is
Right.
up.
But there was nothing because there was the wind area on that particular arm all by itself, and because there was nothing to dampen it other than itself, it shook itself to death basically, and fell off, and cracked and fell. It was in the road was under construction, so there was nobody there. Luckily at that time, that 60-foot arm had come down.
When it did come down, was it a rapid failure or a slow failure?
I don't know. All we knew is that it was on a pole that we had designed for the specifications for that particular city, and it had a fatigue, I think it was a fatigue-free condition, and it came down on us.
See, the reason I asked the question is it's of interest to us when you look at it from a risk assessment standpoint. What's the risk? If the progression, if the failure is nice and slow, the traffic can say, oh, I don't think I'm going to go under that, rather than that. Right. Well, then that, we can take a higher risk.
That horizontal damper has been approved and tested in Texas, and that one has been approved by Texas, in Texas, from their testing. AASHTO has approved that has done that horizontal sign blank that's at the end of the arm, that has done a lot to reduce down that movement in the mast arms. You have to place it above, so you have to have it above your signal. So your mast arm is at this location right here, the signal may be right here. You have to have the dampener above that, because what it's doing is it has to be in line with that galloping motion in there. It can't be at the same location as the arm, as the arm and the signals, because what's happening is it's not being utilized as a sign. It becomes almost a wing. It could actually aggravate it even more.
Well, Carl had an interesting viewpoint for this. He says he thinks it turns into laminar flow going through there. Laminar flow helps to stabilize the vortex. And so I think he's right. And we've done that too. We have it in our standard. We call it that. If you have a problem, put it out. Don't put it
Right.
on.
And that's why we suggest that when you have your inspection and your maintenance and look at that stuff on a yearly basis or that type of thing, that looking for all those types of things, I think that really can tell you which poles are having problems, and then you can put up the dampeners or the sign blanks on those particular locations.
Well, actually, our telephone will tell us when we have a problem.
Yeah, I'm sure. If you call right away. Anyway, that's all we had is for our kind of brief presentation for the different structures and how they compare, and a little bit of a very generic vibration thing, and just to kind of show some generic things about the vibration and how just very variable the whole vibration and frequencies and all that kind of stuff is. So we'd like to take a break for a little bit before Jack goes into the final little parts of our little presentation today for you all. So we'll take like a 5-minute break or so.